In this lesson, we are going to discuss the basic applications of integration, and hopefully by the end of this lesson, you'll be able to solve some initial value problems using the definite integral concept and apply the net change theorem and then calculate and interpret the average value and so on. We start the lesson well, I guess the big lesson plan here is to introduce completely out of context a few new results. Then we'll see how these results can be applied in the analysis of the rectilinear motion, something that we are already familiar with. And then finally, we will extend our perspective and discover how integration serves as a powerful tool across many other fields and real-world scenarios. That's the plan. But we start by solving or revisiting the initial value problems. What is an initial value problem? We encountered initial value problems for the first time when we were introduced to indefinite integrals. The initial value problems are the types of problems where we are given the derivative. So we have a derivative of a function, and we are given a condition that the antiderivative of this function satisfies, and the task is to find such function among infinitely many antiderivatives of the function. So that's what we called initial value problems. And in the past, we solved these problems by following the process. First, find an antiderivative, then find the general antiderivative, then plug in the initial condition to solve for C, and then use that value of C to write your final answer. So let's try to do the same thing now, actually knowing the definite integral as a concept. And we start off by writing the general antiderivative, but the general antiderivative can be expressed using the definite integrals in the following way. So we're going to write the antiderivative, as a definite integral that goes from a, some arbitrary value a within the domain, so that the function is defined everywhere between a and x. And we can write the general antiderivative like this. Now, that was step one. Step two was to turn it into the general antiderivative, and I guess we do that. We already did those two steps here, but step one is complete, and now we can complete step two by adding this constant, which serves as the constant of integration. And this is what we would call the general antiderivative. Now, in step three, what we do is we plug in the initial condition into this equation, and we solve for C, this C. So we're going to plug in x0 and y0 everywhere. And we're going to solve we're going to set it equal to y0, and we're going to solve for f of a. F of a will be equal to y0 minus integral from a to x0 of f prime t dt. This is the constant that makes this antiderivative to satisfy this condition. So in the last step, we just have to replace the constant in the general antiderivative with what we found it to be. So instead of writing f of a, I'm going to write plus y0 minus integral of a, an integral from a to x0 of f prime t dt. And this is the best part, where we can combine this integral and this integral together by undoing the subdivision property. So when you integrate from a to x and then subtract the integral from a to x0, you're essentially left with the area that goes from x0 to x. And this is the antiderivative that, well, A, it is an antiderivative, and B, it satisfies this condition. Therefore, this is the solution of the initial value problem. So what happens is that instead of having a four-step process, we can now code this formula into some computational device and produce the answers to initial value problems using the formula rather than using the process. So one more time, let's write this formula. The solution to the initial value problem will be the definite integral from x0 to x of the given derivative plus y0. However, you don't really need, as a human, you don't really need to memorize this formula because you can always rely on that process, which is much more intuitive than this. However, it is really hard to ignore the elegance of this formula. So this we're going to call the first application of the integration. We can use integrals to solve initial value problems given the condition. That means when we given velocity, we can now find the position function as long as we know position at some point. Given acceleration, we can now find velocity function as long as we know velocity at some point. This is the power of this application. Next application that we're going to demonstrate is called the net change. And let's recall the definition of what the net change is. The definition is pretty straightforward, so while I'm copying it here, you can spend a second thinking about what it would be, and here's the answer. This is what we call the net change. The net change of a function is simply the difference between the outputs on at the boundary points of an interval. So the net change of f of x is simply f of b minus f of a. In applications, the net change could mean the net change in population, revenue, position, and so on. Previously, we have learned how to estimate the net change using differentiation, and in particular we use the concept of differentials and linearization of a function to estimate the net change. However, we revisiting this concept, and now that we know integrals, and we produce what's called the Net Change Theorem that says if the function is integrable, then the net change is this. The Net Change Theorem offers an alternative way for finding the net change, obviously. We don't have to use the definition. We can actually now use the integral. However, the range of applications, or the range of scenarios in which you would want to use the net change theorem, is slightly different from the range of scenarios in which you want to compute it directly and the range of scenarios in which you want to approximate it. We can use the net change theorem when the rate of change function is given. So that means when we're looking for the displacement, and we're not given the position function, but we're given velocity function, then we can use the net change theorem. And let's take a look at how it all works out by doing an example. Let's compare the net change. So let me put this problem here. Compare the net change We're experiencing some technical difficulties here. There you go. So this is an example. And let's see, what is the net change theorem all about? So first we're going to compute the net change by simply evaluating f of 5 minus f of 2. F of 5 is 1 over 5 squared minus f of 2, it's going to be 2 squared. So it's 1 over 25 minus 1 over 4, and it's going to be what? 4 minus 25, negative 0.21. That's the exact answer. We can also approximate it using differentials or linearization of this function, but this is not about that. This is about using the net change theorem. But I just want to point out that we do have that skill in our toolbox of approximating this with differentials or maybe linearization. Now, to apply the net change theorem, we have to set up the integral not from some generic a and b, but from 2 to 5 of the derivative function. The derivative of 1 over x squared is obviously negative 2x cubed. So when we write negative 2x cubed here and we set up this integral, we integrate it using the rules of integration. So we have x to the negative 3 dx and negative 2, and then antiderivative of this is what is it? It's x to the negative 2 over 2 over negative 2, and then we evaluate it from 2 to 5. And now we simplify this. We also have this, so negative 2 goes away, and we have 1 over x squared evaluated between 2 to 5. And as we're applying the fundamental theorem of calculus here to solve this integral, we're actually realizing that we literally ending up with the same exact expression. So the net change theorem, it's not that big of a breakthrough. It's just spinning the fundamental theorem of calculus around and rephrasing the result. So of course we're going to get the same answer, which is 0.21, negative 0.421. So we are now capable of using the net change theorem. Now I want you to pause. Well, actually, let me write the problem first, and then we'll pause. But go ahead and find the net change of this function using two different ways. So one way will be to, again, pause, and in 3, 2, 1, I'll tell you the answer. So 3, 2, 1. One way to find the net change is to evaluate f of e cubed minus f of e, which is ln of e cubed minus ln of e, which is 3 minus 1, which is 2. Another way is to integrate from e to e cubed the derivative of this function, which is what? 1 over x ln, there's no ln, dx. Now antiderivative of 1 over x, it's ln of x, absolute value of x, from e to e cubed, and then when we plug everything in, we end up again with exactly the same expression. So both answers are 2. But the point is, well, again, as I said earlier, the main range of scenarios under which you would consider applying the net change theorem is when derivative is given and the function is not given. So here it seems backwards to go from the function to the derivative and back to the function, but it feels more natural when derivative is given and you have to go back to the function. So the way we go back to the function is through different integration process, and in that case the net change theorem seems to be a more intuitive approach. The net change theorem offers now an alternative let's see. Way for finding, actually scratch that, I already said this. So what can we do now in terms of applications with the net change theorem? We can now find displacement when velocity is given. So we don't need to have a position function, we need velocity function, and we can now find displacement. And let's write this down. So if we're integrating the velocity function from t1 to t2, we're going to get what? We're going to get the st2 minus st1, which is what we call displacement. This is something that was not intuitive when we initially were introduced to the rectilinear motion. We did learn how to find displacement from the graph of the position function, but not from the velocity function, and now we can do the same with the velocity function. However, if you recall, there was an adjacent concept to displacement called the total distance traveled. And to find the total distance traveled, we had to look at displacements on the intervals where the object was moving to the left or to the right, and to account for all those differences. If you want to find the total distance using integrals, there is a way of setting it up. We simply have to account, as I said verbally, we have to count all the negative displacements as positive displacements, and one way to count negative as positive is to apply the absolute value. So this integral is a nice expression to represent the total distance. And let me ask you, based on this conversation, how would you interpret this? Let's say the integral from t1 to t2 of acceleration function. And how would you interpret, I'll let you think about it for a second, this. Okay, in 3 to 1 I'll tell you the answer, but feel free to pause the video and take a moment to think about what does this mean. And 3, 2, 1. This, according to what we just learned by stating the net change theorem, has to be the net change of the antiderivative of a, which is velocity. So this is going to be velocity at t2 minus velocity at t1. So this is not the displacement, but this is the net change in velocity. So by integrating acceleration function from t1 to t2, we'll find by how much velocity have changed since t1 to t2. Now, the addition of the absolute value somewhat complicates the interpretation. It may not be intuitive anymore. It is not as intuitive as it was for the displacement versus total distance comparison. But the proper way to interpret this is to say something along the lines that this quantity represents the total change, and by total change we understand that we're going to count negative change as positive change of what quantity? In this case, velocity. And we have to specify the time interval between t1 and t2. Now, this is not as intuitive, as I said before, as displacement versus total distance. However, one way to imagine this quantity is to think of some measuring device, in this case measuring device of velocity, some meter. We have such meters on the cars, like it's called speedometer. But imagine if the car was going in reverse, and then speedometer would go in the negative side of the gauge. Like imagine like if velocity could have been negative 20 plus 30, right? And then this total change of velocity can be associated with the total distance traveled by that arrow that shows you the speed in the speedometer, right? It won't be exactly the distance, but like it correlates with that distance. So another way to look at it is to imagine like those bars. Sometimes when the music plays, they measure the loudness of the music with those horizontal lines jumping up and down, right? So imagine that was the way to measure the velocity. Like if you accelerate, it goes up. If you decelerate, it goes down. So this quantity right here will, I guess I could have drawn this, right? I'm showing it to Nobon with my arm movements, what it looks like, but I should have just drawn. So imagine this was the velocity that could go up or down. And at any given point, you can tell what velocity is by looking at the level. So this quantity will represent the total distance traveled by this horizontal line segment. That's one way. Again, it's not intuitive, but it is an interpretation of this quantity. Anyway, let's move on. We're going to move on to the third application called the average value. We're going to start off by introducing the average value, and I guess I don't need to, I'm still going to remind you, but this definition looks silly and definitely not calculus-like. But the average value of anything is the sum of the values divided by the number of the values. So when it comes to computing the average value of the function, what would it be? It will be the outputs of the function at various points divided by the number of the points. And if you want to find the true average value, then you have to send n to infinity, because continuous functions do have infinitely many points. If it was a discrete function, then we would have gotten away with just the finite sum, but here we have to make it infinite. And let's take a look at this expression. It seems very non-trivial. It's like, what the hell is this? But with a little manipulation, we can introduce sigma notation in the numerator. So we have sum of f of xi as n goes from 1 to, well, as I goes from 1 to n, and then we're dividing it by n, but n can be expressed as b minus a over delta x. Remember the formula for delta x? It's b minus a divided by n. So n is b minus a divided by delta x. In the next step, we're going to do two things. We're going to move b minus a from inside of the limit outside, because it's a constant, and we're going to move delta x to the numerator. And what you see, you should be able to recognize it. What is this? This is the limit of a Riemann sum, and based on what we have studied in this class, it can be, well, not in this class, but like recently, like 2 lessons ago, this limit is exactly the integral from a to b of f of x dx. So the average value of a function can be found using this formula right here. So this is the formula that one can memorize, but now that I showed you where the formula comes from, hopefully it will make it easy to remember. We simply take the integral and dividing it by the length of the interval. With this formula, we can now find the average of not every function yet, but of many functions. So let's find the average value of this function on this interval. So how do we do that? It's very simple. The average value of the function is equal to 1 over b minus a times integral from a to b of the function. As long as you know the antiderivative, you know how to find the average value. So here pi over 3 is what? 2 pi over 6, so it's like 6 over pi. And antiderivative of secant squared is tangent x. And by the second part of the fundamental theorem of calculus, we rewrite this definite integral like this, and then plug it in. So 6 over pi times tangent of pi over 3 minus tangent of pi over 6. Let's see, what is tangent of pi over 3? It's sine of pi over 3 divided by cosine of pi over 3. Sine of pi over 3 is root 3 over 2. Cosine is 1/2. And for tangent of pi over 6, it's the other way around. It's 1/2 divided by square root of 3 over 2. So the final answer is 6 over pi. 2's go away, and then we have, so what is this? Root 3 minus 1. So it's 3 minus 1, 2 over root 3. We can rationalize the denominator, so it becomes 4 red 3 over pi. Something like this. That's it. So the point is, application is pretty straightforward. It's, you gotta remember the formula. The rest is calculus, like calculus of integration. I'm going to give you another problem, another problem to try, and feel free to pause the video and work on this problem, and I'll tell you the answer in 3, 2, 1. I guess 3 to 1 is now. So to find the average value of this function, we're going to set up the formula. So it's going to be 1 over pi over 2 minus 0 divided, multiplied by the integral from 0 to pi over 2 of sine of x dx. And we have 2 over pi negative cosine x from 0 to pi over 2. So it's 2 over pi negative cosine of pi over 2 minus negative cosine of 0. Cosine of pi over 2 is 0. Cosine of 0 is 1. So we have 2 over pi times 1. So the answer is 2 over pi. So make sure you got the right answer. We also now state what's called the mean value theorem for integrals. We have seen the mean value theorem for derivatives before, so at the end of this course you should make sure you're not confusing those two. The mean value theorems for derivatives told us that if you have a function, there is a point where the slope of the tangent line matches the slope of the secant line. And the secant line is called the average rate of change. Why is it called the mean value? Because we guaranteed to have the point where the instantaneous rate of change is equal to the average rate of change. The mean value theorem for integrals does say the same thing. It says there exists a point where the output of the function is equal to the average value of the function. So, but given that the average value of the function is this, the statement of the mean value theorem, the complete statement looks like this. But this is the important kind of intermediate step, which makes it mean value theorem, not just any other theorem. Why is this true? Well, if you think about it visually, what is the average value of the function? So you have a function on the interval from a to b, and the mean value, it's such output that you can use the rectangle of that height to approximate, or not to approximate, but like to actually equal the area under the graph. So if there is such rectangle, then this we call the average value of the function. That means we can replace, from the integral point of view, we can replace that function with just an average value here. And from the integral point of view, nothing will change. And by the integral point of view, I mean from looking at the area under the graph, nothing will change. So you replace the function, but the integral wouldn't care because the area is still the same. It's in the same spirit of the mean value theorem for derivatives. You can replace any function with a straight line going from this point to this point, and from the derivative point of view, nothing will change. The derivative will be the same. It's just instantaneous rate of change will be the same to the average rate of change at every single point. Here's the same thing. The output of the function at every point is exactly the same as the average function on the whole interval. So this is what we call the mean value theorem for the integrals. It guarantees that such value c exists. So what it means is that when we're solving problems like this, we can actually answer a slightly modified question. We can say, find the average value of the function and actually find where it occurs. So to find where it occurs, we need to set up and solve the equation f of x equals to, it's not going to be f of x, but it's going to be f of c equals to the average value. So in our case, it will be secant squared c equals 4 square root of 3 over pi. And to solve this equation, solving this equation will give us that value of c. You just have to make sure this value is in this interval. Solving this cannot be done like let's see if we can solve this analytically. So secant c is equal to square root of 4 square root of 3 over pi. That's secant c. So cosine of c will be equal to reciprocal of that. So it's going to be square root of pi over 4 square root of 3. And now solving for c means we're going to find the arc cosine of square root of pi over 4 square root of 3. And in general case, like we would have to do like this kind of stuff plus pi n, right? But we know, because we are in the first quadrant, it suffices to just write this, and this will be the answer. To show you that, I'm going to open Desmos here on my other screen, and I'm going to do it first myself, and then I'll show you the result. We're going to graph the f of x. F of x equals secant squared x. We're going to graph it on the interval from pi over 6 to pi over 3. So I'm typing all this up. Pi over 6 less than or equal to x less than or equal to pi over 3. That's what the graph of it looks like. If we're looking for the average value, we have to set up the integral from pi over 6 to pi over 3 of this function. And I got the answer. And now I'm going to make sure it's the right answer for square root of 3. Hopefully it's the right answer, right? Hopefully we didn't make a mistake. No, it's the wrong answer. Somehow I'm missing... I don't know what I'm missing, actually. Hold on. Tangent... Did we make like a... Square root of 3... We find the common denominator, square root of 3, so it's 3 minus 1, 2... I don't know where I made the mistake. Pi over 3... Oh my god. I forgot to divide by that b minus a thing. So I just found the integral, but I forgot to divide it by pi minus 3 minus pi over 6. Now the answer is correct. And so let me show you that. So this is what Desmos says, which confirms that we done this problem correctly. But I want to also show you that this is the correct answer. So if you look at the graph of this function and you plug in arc cosine of square root of pi over 4 square root of 3, and you introduce another function, g of x, let's say, that is equal to that average value on the same interval. The average value of that function let me see, it's giving me some issues. It doesn't like constant functions inside of the piecewise functions, but let's see. For some reason it just doesn't like it. G of x equal... Maybe it doesn't like the lack of parentheses. Let me try again. I know it's not the most exciting part of the lecture, but let's see. Did it work? No, it did not work. But can it compute it? It does compute it, but setting y equal to that does produce the graph. Yeah, there you go. So I think I'm ready to show you the outcome. Oh boy, it doesn't like this part. This makes no sense. There you go. There you go. Alright, so I just need to remove this part. Alright, there you go. So what I'm going to show you is what you should be able to see on this Desmos demo. Let's take a look. This is the function. In purple we have the average output, which is 2.2 something. And this right here, this point right here, is where the function, it's the input. So if we project this on the x-axis, this is the input where the function reaches its average value. So if you integrate the purple line, which is what I did here, and compare it to the integral of the red line, you'll get the same exact answer. And that's exactly what we see. Now we can pause the video and ask you to find the value of c at which this function reaches its average value. And to do that, what do we need to do? We need to set up and solve this equation. Sine of c is equal to 2 over pi. So c is equal to arc sine of 2 over pi. So we, using the formula, can find the average value, and using the theorem we can guarantee that function achieves that average value at some of its points. And then we can use algebra to find at which point the function achieves its average value. Now, from the point of rectilinear motion, what does this allow us to do? It allows us to find the average velocity of an object on an interval given the equation for given the velocity function or the position function. At this point we can navigate from the position to velocity to acceleration and back given some initial values. So let's find the average velocity of a particle whose position function is given. First of all, we have to acknowledge that the average velocity will be the 1 over b minus a integral from a to b of velocity function. So we're given position, we're not given velocity, but we can use calculus to find the velocity as the derivative of the position. So the position is given, derivative will be -4 plus 2t. And now to find the average velocity on the interval from 0 to 3, we simply apply the formula. 1 over 3 minus 0, integral from 0 to 3 of -4 plus 2t dt. We don't have to spend time looking for this antiderivative because it's given to us, but we don't even have to use, this is an antiderivative. This is a particular antiderivative, so by ignoring this 4 we'll get an antiderivative. So an antiderivative is -4t. But at the same time, you look over here and you just look at this function and just use the anti-differentiation technique covered in one of the previous lessons, and you just see how it just matches. So it doesn't matter how you think of it, you're still going to get the same answer. And the integral is from 0 to 3, and we're almost done. 1/3 -4 times 3 plus 3 squared minus -4 times 0 plus 0 squared. So the final answer will be -12 plus 9, -3. -3 over 3 is -1, whatever the units are. Distance units divided by time units. Alright, so we found the average velocity of a particle whose position function was given. Now, pause the video and answer the same question. Let's try to answer the same question. But I'm going to give you the acceleration function instead. So if a of t is given and a of t is 1 plus 2t and the interval is from 0 to 5, can you find the average velocity of a particle? I'm going to pause while you're thinking and then I'll answer this question in 3, 2, 1. The correct answer is no, we cannot find the average velocity. Why? Because the average velocity is given by this formula. But we don't know v of t. You may say like, well, why don't you find it using a of t? But to find v of t from a of t, we need an initial condition to be given to us. Otherwise, we just cannot narrow down infinitely many curves to one that we're looking for. We cannot find the average value of infinitely many curves. That task makes no sense. So we cannot complete this task. However, if the initial condition is given, then we can complete the task. So now, given that v of 0 is equal to 1, can we find it? The answer is yes. So we're going to have to do the preliminary step of finding the velocity function by solving the initial value problem. So velocity at time t is given by the integral from 0, again, we using this formula right here that we discussed earlier, the integral from 0 to x, or in this case to t, and we have acceleration function given. I cannot use variable t inside of the integral. I'm going to use x plus y of 0. Y of 0 in this case it's 1, so it's going to be plus 1. So again, let me write this formula in general. So it's going to be v0 at, oopsie, not v0, t0 at, and we add v0 over here. And now we're going to plug everything in. So we're going to go from 0 to t. A of x is 1 plus 2x dx plus v of 0, which is 1. And let's solve this. So we have 1 plus 2x. The antiderivative is x plus x squared from 0 to t plus 1 is equal to t plus t squared plus 1. And now we can finish this problem. So we can find the average velocity by applying the formula for the average value of a function. So it's going to be the integral from 0 to 5 of t plus t squared plus 1 dt. And the answer is 1/2 t squared plus 1/3 t cubed plus t evaluated from 0 to 5. At 0 it's 0, but at 5 it's going to be 25 over 2 plus 125 over 3 plus 5. So we can remove this 5 from everywhere. So it's going to be 5 left here, 25 left here, and 1. So the final answer is 1 plus 5/2 plus 25 over 3. Common denominator is 6. Let me take it over here. So we have 6 over 6 plus 15 over 6 plus 50 over 6. So the final answer is 71 over 6. That's the average velocity. All right. Similarly to how we extended the formula. Hold on, have we extended this formula? Yes, we did, right? So similarly to how we extended the application of the net change theorem and the formula, application of the formula to the formula with the absolute value, we can similarly make the same extension and introduce in the context of rectilinear motion, we can find the average speed. So to find the average speed means to integrate on the interval from a to b, but we're not going to be integrating the velocity function. We're going to be integrating the speed function, which is the absolute value of the velocity function. And integrating absolute value functions is something that requires the application of subdivision property, meaning we have to find out where v of t is positive and where it's negative. And whenever it's positive, we're going to be using all of those with positive sign, and we're going to be subtracting everywhere where v of t is negative. But this split is possible by subdivision rule, or subdivision property of integrals. So the point is, using definite integrals and some of these results, we got some pretty interesting applications out of it. All right, so let's move on. In the past, we have learned some of the applications of derivatives in the context of rectilinear motion, and then we generalized those applications from rectilinear motion to other fields and branches of science. And we're going to do the same thing with calculus of integrals. So before we generalize all of these applications to other functions, let's summarize everything that we have done in the context of rectilinear motion. So this is what the summary looks like. We now know how to compute position from velocity. Velocity is the rate of change of the position. We now know how to find the displacement and the total distance traveled given the velocity, which is the rate of change of the position. And we also, using this formula, can find the average velocity and the average speed. And if you already know the position, you can also find the average location of the particle in a rectilinear motion. So this is what we know. Next step we're going to do is we're going to generalize these applications to other contexts and branches of science. And before we do that, we're going to acknowledge that the integration of the absolute value of a function may not always be as intuitive as it is in the case of velocity. So for example, integrating the absolute value of the rate of change of the population function may not be as easy to interpret as integrating the absolute value of the velocity, which is speed. It is possible, and one way is to do this example that I told you earlier. Think of whenever you're interpreting the integral of an absolute value of a rate of change of some weird function. Think of some measuring device that measures that function, and that what you'll get by integrating that absolute value, it's the total distance traveled by that, whether it's an error or some level throughout their measurement process. So that's what this would mean. However, that being said, we're going to focus on generalizing these results without the absolute values, assuming and trusting that you can make that transition when needed yourself by understanding the difference in the meanings between not using the absolute value and using the absolute value. So what we're going to do next is we're going to take this table. By this table, I mean this table. Let me give me one sec. By this table, I mean this table. Why is it doing this? Why is it doing this? I don't know. Let's take this table, bring it here. Let's make it bigger. Let's take a look at what's in the table. What we see in the table is first kind of the general formulas that we know. That is, in general, if the rate of change is given, we can use that rate of change to solve the initial value problem and find the function. We can also use the Net Change Theorem and find the displacement, and we can use the mean value formula to find the average value using the actual output of the function and the rate of change. Now, in the case of rectilinear motion, what does that mean? That means given velocity, we can find the position using this integral, or displacement, or the average position, and the average velocity. So that's what we can do. And that skill, like I said, is not unique to rectilinear motion, and it can be done in other contexts, such as these ones. I don't know what else going on here. So let me duplicate this slide. Let me delete this and let me bring this table right here. And let's make it bigger. Let's make it even bigger. And let's take a look. What do we have here? We have different contexts. In different branches of science, such as economics, this is biology, I guess, this is chemistry. And in different contexts, you may be given a function representing a rate of change of another function. So in economics, you could be given marginal revenue function, which is the cost of, not the cost, but revenue from producing and selling an additional unit. Or it could be marginal cost or marginal profit. It could be rate of change of concentration and so on. It could be rate of change of balance in your banking account or your investment. And when the rate of change is given using the integration, and in particular the skill of solving initial value problem, we can go back to the original population or original function. In this case, it's a population function. In this case, it's the revenue function itself. In this case, it's a concentration. And in this case, it's an account balance. And then we can use the net change formula to actually find a meaningful quantity by integrating the rate of change function. So in this case, we'll get the net change in population and so on. And after that, you can integrate either the original function or the rate of change function to find the average value of the original function or the rate of change function. So you can find the average population by integrating the population function, or you can find the average rate of change of the population by integrating the rate of change of the population. So everything that we've learned in the context of rectilinear motion can now be used in many other contexts, and there are literally infinitely many of them, potentially. We're definitely not going to discuss infinitely many of them, but potentially there are infinitely many other applications, understanding of which is entirely based on your understanding of this table and your ability to make the analogy between the function that you're analyzing and the position function in a rectilinear motion. So, this is the end of the lecture. In summary, we have learned that integration is far more than a tool for finding the geometric areas or solving motion problems. It is a universal language for describing accumulation in general. And whether we're tracking a population or revenue or concentration in some chemical balance equations or balances in the investment portfolios, the same mathematical framework applies universally. By recognizing these connections, you're gaining a way of thinking that will serve you well across many disciplines and in any field where change and accumulation matter. Let's end here. If you have any questions, now I guess it's time to practice, so if you have any questions, feel free to reach out.